I think that's at the time of the day, everyone knows what is an albedo, and of course it's good to know that there is some stringent needs about albedo, and that you need to, we need to work very hard to make this accurate albedo as possible to answer the requirements. So yes, my background is mostly to work on development of surface albedo from space. I don't want to make a review of albedo. There are so many products at different scale, notably core scale resolution, and Peter mentioned MODIS, but there is other albedos that cover all the globe. The challenge is because, some decision makers and some management have to be undertaken at the crop scale. We need to define an albedo that answer to the needs. That's the reason we are looking now at how we could do an albedo product from Sentinel-2 and Landsat-8 over time. And since of course, there is a gap to be filled. Next. Okay, next.
Okay. I clicked on the second one, so you should have the overview now.
Yeah, when I say next, that's fine.
No, we don't see it for the moment.
You don't see it?
No.
Why is that?
Try the PowerPoint maybe instead of the PDF.
Ah non, reprendre le partage. The sharing part seems to be on break from my side, and I don't understand this.
Can you?
That's
nice.
The sharing part is on a break. Well, I'm sharing my screen. Can you see the PDF now?
Yeah, that's. Can you comment before the previous one? Yeah, that's okay. That's fine.
Yeah, I guess it's not functioning if it works.
Just to remember the objectives. That's as to an albedo from combining Sentinel-2 and Landsat-8, and we'll see that's not an easy task for different reasons. The reason is because actually what's available on the market is coarse resolution for MODIS, VIRS, PROBA-V, and now we have Sentinel-3. And especially we know that actually the needs are required for agriculture area. Also, we have seen some presentations that mention the forestry. Urban is also on the stage because there is also some climate mitigation that could be handled. Okay, so the challenge is to make the agricultural practice more efficient and compliant to climate mitigation. Next one. Okay, so I can pass shortly on this one for two reasons. Of course, there is always some talks that demonstrate that actually climate mitigation about greenhouse gas effect could come from intermediate crops. This is where we're working on, try to take some decision that during the winter time we don't have any land surface with bare soil, but instead we have intermediate crops because albedo will have some gain. If only at the European scale, if the decision was to maintain the vegetation all the year long, I say we could be actually really impact on the carbon storage. And my colleague Eric Sichan and also probably will talk this tomorrow in more detail. Next one. Okay, so question of relative forcing was already discussed before, and if you look at albedo on the top and relative forcing at the bottom, and on the right you have a PAI or LAI, what's the plant area index. What you can see here is actually there is a clear connection between albedo and relative forcing, and during period of time when we have intermediate crops, relative forcing is important, and this is for two anchor station, ECOS anchor station located near Toulouse. One but La Masquer. Next one. Okay, so in the national level in France, we to balance the lack of albedo product high resolution, we developed what we call the TIA, which is Land Data Center with Center of Expertise. So we have some topics and particular ECV and all development about Sentinel-2 and Landsat supported by CNES, Express French Agency, and one of them is Albedo. Next one. So like we come to accurate assessment about Albedo. What we can see, somebody put on the table that 0.05 absolute Albedo could infer relative flux about 10 watts per meter square. So we need to have an accurate assessment of Albedo, and for such reason we need to go through all pre-processing that converge to increase the precision of Albedo, and atmospherical correction is one of them. Just to mention that also in the way we define the Albedo, we were concerned about atmospheric correction. We have a MAJA method developed and supported by CNES. Next one. Okay, so we come to the real true story. So when you have, we define a remotely synced Albedo, we have actually four resolution to comply. One is spatial, the one is spectral, the one is temporal, and the directional resolution. Directional is important because you need to integrate the reflectance over all directions to calculate the mean reflectance, which is actually an Albedo. If you look at Sentinel-2, for instance, you have a spatial resolution and spectral resolution, but temporal resolution is not enough. Even with two satellites, we have one data every 5 days in best condition. I mean clear sky condition, which is not often the case. And so we don't have the directional resolution because we had a narrow field of view, 12 degrees, and we cannot really infer information about anisotropy of the targets. Ideally, coarse-scale resolution satellite like PROBA-V and Sentinel-3 or MODIS, they have the suitable spatial, the suitable spectral and temporal resolution. But of course, they don't have the spatial resolution we like to have to cope with the crops. Next one. Okay, so if you look at the different satellites in terms of spectral bands, normally there is always a possibility to find a band that overlaps, such that you can jump for another band, one band for the other one, and switch, such that you can define equivalent band between different satellites in reference to the solar irradiance. Next one. Okay, how do we do that? So we run relative transfer modelings, and here you have an example with famous PROSAIL code. So we can simulate actually mini canopies. I did the exercise for more than 6,000 canopy, and we define properties in chlorophyll, carotenoid, and so on and so forth, leaf area index. And based on this, we simulate the reflectance and different spectrum of different sensors, and we try to define some conversion coefficient. Next one. Next. Yeah, okay, great. So this example on the right, so this is a design of the post-PAIL model with different layers, with which is a diffuse layer with homogeneous layer of leaves. What you can see on the bottom of the graph is actually if you try to convert the true solar albedo to narrowband conversion from some bands, you can do so based on these models. So it means that with a few spectral bands, you are able to obtain what we expect in terms of relative forcing as a solar albedo over all solar spectrum, are defined on the graph on the left for solar irradiance. So okay, so this is a good point that we don't need to have hyperspectral measurements to define albedo. Only some bands will be in the right part of the spectrum will be enough. Next one. This is a conversion coefficient. So you see that it's about a few percents between different satellites. You have a conversion between Sentinel-2 and Landsat or PROBA-V. And this, even if it is a little, as important, because actually this is we need to cope with the expectation of the users, just to take some decision about the relative force. The next one. Okay, so actually, if you would like to have an albedo, we need to define first what we call a BRDF, bidirectional reflectance distribution function. What the BRDF tell you about directional property of any Earth target, and this is proper information of any crops, any forest, any soil also. So actually, this can be quite complex because that's a combination, especially at core scale, of different landscape attributes. But by chance, we can resume this to this all this directional signature to some generic signature. Here you are from left to right. You can see some backscattering from bare soil, for instance. You can see it look differently if you look back to the sun or if you look forward to the sun. You can also find some specular reflection of, for instance, for sunflower or soybean, or for maize leaves also. So there is some specular effect, and also you can have some for dense canopy like forest. You can have some what we call a volume scattering reflectance. So the combination of generic, the BRDF signature is quite nice, because it means that we can have some generic approach to model BRDF albedo at the landscape scale and as globally. Next one. Okay, so if one would like to model albedo, there is different options. One option is we work locally to have a 3D model. This is ideal because you can, you can define the optical and particular the structural property at different scales with different index and clamping and so on and so forth. So probably that's a broad scale, you're not able to, you don't have such information about architecture. Another issue, if you would like to model albedo at the landscape scale, is to define some of albedo for different homogeneous medium, like using the PROSAIL scope model. But you'll see the most widely used, most applied method is based on kernel-driven model, and they were used for MODIS, Metosat, MIRIS, and so on and so forth, and now for this. Next one. So the approach is one I developed during my PhD about some time ago. So you can imagine one remote sensing pixel can be disentangled between an isotropic component, volume scattering component, and geometric effects. So you can add an aerosol component if you like to, and also a specular component for snow. So based on that, we have what we call a linear system, which is nice because we suppose that it's just an adding of elementary photometric consideration. So it's a linear system, and we have a matrix with some a priori information. And the purpose of that is to have a recursive procedure with a state variable between the kernel, the matrix of the kernels. Next one. So one key question is about gap filling. So of course we do not like to have gaps, but we have high level of cloudiness, especially in certain areas, and you can have a lot of time elapsed, so we don't have any data. The strategy is to start from a priori information and to repeat the product with time. Every time we have a new information, we refresh the product, but for security reason, I will put some weight to the a priori information, weight to the innovative information. And this is weighted by the time constant, and we can play with the time constant. So if you like to have a constant product, we have what we call a sliding period of time. So every 10 days, we consider some data, we make the product starting from a priori information, which is the last albedo product. So next one. Okay, rapidly, this in French, but mostly understandable. So this is a flow chart about, so in input, we have some top of canopy reflectance different resolution from Sentinel-2 Landsat. we perform an inversion of BRDF model. And then we have some BRDF parameters spectrally, is all spectral bands. Then we perform an angular integration, and from that we can develop at the end a spectral integration to derive the albedo at different resolution in visible, infrared, and solar. Next one. Okay, so the albedo needed, that's directional-hemispherical reflectance, bi-hemispherical reflectance. And we also need to have broadband albedo in the visible, 0.4, that's the PRR for people that know, to 0.7. That's where we make conversion to carbon stuff. And we have one for energy balance in solar. If you look at the bottom, that's a template taken from GCOS that tell you about requirement for albedo, for DHR, directional, and for BHR. And actually, the one albedo that's really needed, that's what we call a blue sky albedo. That's a combination of both, weighted by the diffuse component. That's the sky radiance. And you see that actually what's important in terms of frequency will be to have a daily albedo, ideally resolution of 50 meters to comply with the crop scale, and of course to have a precision max of 5%. So this, I mean, this is a very essential requirements. Next one. Okay, so all the method is available if one would like to go through in a paper that appeared about 2 years ago, and that was developed in the frame of the Copernicus Global Land Services, with as a cooperation between different institutes, and that was produced as Vito in Belgium. And this all for PROBA-V. So next one. So I can give you some example of having the method, persistent method for mapping albedo. So you see here, you can see that for Ancho station located in Spain near Valencia, where you can see actually you have a continuity of the product almost for visible, infrared, and broadband. And reason for that, no gaps, is because actually we use a recurrent algorithm with a priori information. And that's instead of what you could see sometimes with MODIS, that's the timing of the product. Actually, what we do, we put the time of the product and in the medium of the scale or median scale of the set of clear sky data. And that's very important in terms of timing, because if you can say the edge effect as an important, because you can have a time shift if you don't locate correctly in time the product based of the data you use to make it. So next one. So that's a comparison between albedo from Copernicus and MODIS. Scatter plot on the right, you see that actually they're pretty good compliance between the two products. And on the left, you have for 2014, you have a comparison of the difference of the products, and you can see that the top from that's for an infrared. Both for an infrared, you can see you have a little difference between the two products. Next one. Okay, the question about having data to make a product, and so in some period of year and some geographic location, the fact is we don't have many products. That's particularly true in Scandinavia in November, and or even North Europe. And you say that we need to wait about 3 weeks sometimes to accumulate information, even with orbit satellite that pass every day because of just the cloudiness. And you can imagine that's for heliosynchronous and core scale resolution, but you can imagine for Landsat or Sentinel-2, which Landsat every 2 weeks and Sentinel-2 every 5 days, that actually we are lacking of data, just simply. Next one. Okay, then another point about relative forcing. If you want to estimate relative forcing at core scale, you need to couple with satellites that give you the downwelling radiation at the proper time. And over Europe, we can rely of Meteosat. that give you data every 30 minutes and 3-kilometer resolution, which is quite acceptable for atmospheric radiation. Next one. Okay, so now I would like to show you an example of what we'll be doing for ATCOR station of La Masquère located in Toulouse, which is an ATCOR station. Actually, we have deployment of more than 10 stations around Toulouse with different, that consider different, look at different soil types and so different crops. And basically, we have set up the instrumentation you can see on the picture. And we have some solar panels that I can work permanently, and we have radiometer and albedometer, CNR, looking at cover all the solar spectrum, and we have also some sensor looking at humidity and temperature to run model around the station of reference. Next one. Okay, so that's the first result. That's kind of demo applying the model over the ATCOR station of La Masquère. La Masquère is a maize crop. And what you can see, and that's for Orade actually. For Orade, what you can, Orade is sunflower. What you can see again, actually there was different crops along the year, and you can really see for 2018. The green is data measured on the sites, and the other one is broadband albedo, solar albedo in bi-hemispherical and directional-hemispherical, using the recurrent algorithm. Well, you can see that actually we are not too bad. We need to consider the footprint errors, and the footprint actually was we used 20-meter resolution. Be careful. We need to be careful actually that at such resolution we cannot look really at the pixel of the mast, otherwise we had the mast contribution in the pixel. So it's a difficulty. It's not like a score scale when it's less importance. And at the bottom, you can see actually we can convert this albedo product in terms of relative fluxes, relative forcing for the surface, based using a METOSAT, what you see METOSAT, you see in red, METOSAT incident radiation. Next one. Okay, now we have also a project going on at the national level. So we recently started with putting some anchor station of our prairie. The goal of that is try to, in some way, promote the grazing in France, showing that actually we can have a positive, it can have a positive impact. And we selected different prairies. It's only about prairies of a different location in France, different regions. So it's different category of prairies. Idea is to prove that having prairies can be a mean for climate mitigation in terms of relative forcing. So we like to measure the impact of this on the ground. Combining, the herbs, grassland, and of course the period of bare soil, so the only thing that actually we'll have to show from this project that we can have a smart agriculture and a sustainable agriculture, and that's okay. That we can combine the grazing and actually and also the climate mitigation. Next one. Okay, so I come to my conclusion. So we really start doing this work with Sentinel-2 and Landsat because actually we need to combine high resolution satellites with moderate resolution satellite that we'll be doing with Sentinel-2, Landsat, and Sentinel-3. So in some case, we can make an albedo if we are lucky to have enough clear data in some area, but we can not do it at a continental scale. And actually, this is like we like to do. Actually, we see that if we want to demonstrate that relative forcing is for the surface is is a powerful means to mitigate albedo climate. We need to have constant product, permanent product for different countries and permanently. So one question is about separation about albedo from vegetation and soil. That's something we'll be working on, and I think this is completely the fact we work high resolution is completely compatible. Was not the case with MODIS, for instance, which is more complicated, and maybe we could highlight the impact of each component to make clear what's their contribution in respect to carbon storage. Other thing is, of course, it's important to maintain vegetation all year long. That's a relative effect, provided you have a dark or at least medium bright soil. If you have bright soil, it's not, I mean, a soil that is more reflective that vegetation is not needed. We mentioned before, some people, the combined effect of biogeochemical effect due to soil nitrogen or carbon, but also the relative effect. This is something we like to prove through the different projects. Albedo is the first stone of the wall, but it's not the last one. We have other projects supported by ESA and the European Union. One of them, we have ITT that will be supporting the development of some tools to combine Sentinel-2 and Sentinel-3. Probably Sentinel will be corrected properly from atmospheric effects to meet the requirements. And also we'll have a project in MACCS. We'll look at the albedo and carbon over Europe. So that's a cooperation between Belgium and France. And this will be starting also in shortly, probably next year.